Hey, this is Kyle, and I'm here to talk about the last part of our exam 3. So we're going to use the differential equations we solved for in part B1, and we're going to use it to apply it to a situation where we actually have numbers with respect to the cooling tower, and that way we can kind of show graphs that show how the molar concentration of water changes with respect to position, how the temperature of the liquid changes with respect to position, and how the temperature of the gas changes with respect to position. So the first step, we want to import all the libraries that we're going to use. Import numpy as np. We'll import plotly.io as po. And that's going to allow us to make default changes to the graph, such as the one I'm about to make. So I prefer the graphs to have a dark background, so I'll do that. Plotly dark. Next, we're going to import the make subplots feature, so we can actually make the subplots. And then we're going to need two features from SciPy, from the integrate library. We're going to need solve IVP, and then we're going to need the root from the optimize. So from SciPy.integrate import solve IVP. And then from SciPy.optimize import root. Alright, so this is all the libraries we're going to need. Let's see if looks good. So next we have a lot of we have a lot of parameters and given information in this problem, so I'm going to write all those out off camera, and then I'll come back and explain them one by one, just what they are. So, alright, so now that I'm back, I typed out all the information we're given in the problem, as well as some constants that we're going to need. So the first thing I wrote here is the the heat transfer coefficient, which is given to be 10, and that is in units of watts per meter squared Kelvin. Next, we know the ideal gas constant is 8.314 joules per mole Kelvin. We're given that the relative humidity is 50% or 0.5. Next, we have the specific area, and that was given to be 5 meters squared per cubic meter. Our velocity of the air flowing in is given to be 5. Name that velocity air. And then our liquid flow rate, so that was in kilograms per meter squared per second, is 0.5. The pressure is given in pascals to be 101.325. The height of our cooling tower is 20 meters, and the temperature of the water feed going in to the cooling tower is 70 degrees Celsius, and then we'll add 273.15 to go to Kelvin. And the temperature of our air coming in the cooling tower is 25 degrees Celsius, which will add 273.15 to go to Kelvin. Next, I looked at the Anton constants for liquid water, and we're going to need this to calculate vapor pressures of water at a given temperature, which I'm going to do in 1 second. Add that up here, actually. And then next I have some more constants. So the molecular weight of water I have is 18 grams per mole, which I then took to kilograms by multiplying times 10 to the negative third. I did the same for air, except the molecular weight of that is 29. Then I have the density of air as 1.2 kilograms per cubic meter. Next I have the heat capacity of air to be 1,000 joules per kilogram Kelvin. And then next I have the heat capacity of vapor water to be 2,000 joules per kilogram Kelvin, and liquid water to be 4,190 joules per kilogram Kelvin. Then I have the heat of vaporization of water to be 40,700 joules per mole. And then, as I mentioned, we're going to make a function up here so we can find vapor pressures. Given a temperature, and we can do that with the Anton equation. So the Anton equation, we want to return just the equation itself, and that's going to be 10 to the power of our a value that I typed out. Then it's a divided by, it's a minus b divided by, and then in parentheses, c plus the temperature that we want to give it, so T, except the Anton equation we want it to be in Celsius. So we're going to minus 273.15. Parentheses. And then this Anton equation gives the pressure actually in millimeters of mercury, so we want to divide by 760, and then it'll give us in atmospheres, and then we're going to multiply by 101,325 to get back to pascals. Shift enter. Looking good. Alright, and now with all of the information we have, we can do a few quick calculations. So one, we want the mass transfer coefficient, and as we looked at, I think it was part A1, we can use the Lewis relation. So the mass transfer coefficient will be equal to the heat transfer coefficient divided by rho divided by density, rho air, density times heat capacity, so CA. So now we have our mass transfer coefficient. Next we can also calculate the molar concentration of water in our feed, in our air feed. So we'll say YA feed. And that's going to be equal to the relative humidity, which is one of the given numbers. Relative humidity times, what can I call on our function? PV. Give it the temperature of the feed, so TA feed. TA feed. And divide by, so that'll give us the vapor pressure at the temperature that the feed's at, then divide by pressure. Oh, just pressure. It's PA. Alright. And next we can, so we have our liquid flow rate, 0.5, so we still need to get our gas flow rate. So right now we just have the, I think I forgot to put that number in, I believe. Oh no, the velocity of the air as 5. So we want the flow rate in kilograms per meter squared per second. So we called that G, so we'll say G air, or we can just say G. And and we'll set that equal to, or that's equal to pressure times the molecular weight of air divided by R times PA feed. And that's how you get the gas flow rate. And I believe that that is all the calculations we want to do right now. So now I want to make a variable z plot. And we're going to do, this is going to come in handy when we want to plot, so np.linspace. So we want evenly spaced values from 0 to our height. And since our height is 20 meters, we're going to do 21 values, because then we'll have a value every single meter. Looking good. And we actually also want to make a couple initial guesses that we're going to need for our differential equations and our initial value problem. So I guess I'll make an initial guess for the air when it is coming out of the cooling tower. So we'll call that TA out guess. TA out G. I already used G a lot, so yeah, we'll take out guess. And we can just say that that is, we'll guess 5 degrees higher than the feed. 5 degrees Celsius or 5 Kelvin, same thing. And then we'll make a guess for the molar fraction, the mole concentration of water in the air. So we'll say, what did I call it? YA feed. So we'll say YA out. Guess we'll keep it the same. And the air is actually going to pick up water as it travels through the cooling tower, so we'll do that. YA feed times 1.1, so we'll give it about 10% higher. And I think that's all we need for the guesses for the z-plot. We got our equations. Okay. And actually, in my calculation for the gas flow rate, I forgot to divide by the velocity of air, and that's what's actually going to make it the flow rate that's given in the problem. So we'll put that in there. And I'm going to make an empty variable called for the solution, and we're just going to say for now that's equal to none. And this is just so we can have a global variable solution rather than the one that's just going to come inside of a function later. So that'll come in handy. Alright, so now we can define a function that will introduce our differential equations that we solved for in last part. So we'll just call that function dy for mole fraction, temperature of the water, and temperature of the gas. And we'll feed that function. Oh, yeah, okay. Yeah, so we'll feed that function a position z and 3 variables. I'll just use the letter v. So our variables will, variable v is the placeholder for our initial guesses, so we'll do it in the order we named the function, so y will come first. So we'll say y is our first element in v. W is going to be our second element. Second element in B. and temperature of the gas is going to be our third element in B. Alright, so next what we want to do is we want to, I should have named this something else up here. So this gas flow rate up here is actually just the air flow rate. So what we're going to want to do down here is solve for a flow rate of just the water. We'll just call that GW. And then we'll add the gas flow rate of the water to the gas flow rate of the air, and that's our actual total gas flow rate. So this is going to be, so our YA feed divided by 1 minus I'm sorry. Y feed is our known value. This is going to be y divided by 1 minus the y that's fed into this function, actually. So then we're going to multiply by the gas flow rate of the air and multiply by the molecular weight of water divided by the molecular weight of air. And that is now our gas flow rate of the water, and that's water in the gaseous phase. So now we can add the gas flow rate of the water with the gas flow rate of the air to get our total gas flow rate. Oh, what the? Gas flow rate of the air. Alright, so now we have our total gas flow rate, which we used in a few of the differential equations. So we're kind of going to define some other stuff that we used in the differential equations. So we want our total molecular weight, which we can get by doing the total gas flow rate divided by parentheses gas flow rate of the air divided by molecular weight of air plus gas flow rate of the water divided by molecular weight of the water, and that is our total molecular weight. Next we want to do the heat capacity of the gas, so we'll call it CG. I don't think I have a CG yet. Yeah, we'll call it CG. And that is going to be equal to C air. I think I called that CA, yep. So CA times G air plus C water. C water in the gas phase, since it's going to be the gas, since we're doing the specific heat of the gas. So C water in the gas phase times gas flow rate of water divided by, so that's all going to be divided by, so I'm going to need parentheses, total gas flow, which I have right there. Nope, don't know why it does that. Alright, so now we have the specific heat of the gas phase, the molecular weight, the total gas flow rate, and the gas flow rate of the water that we introduced. So now we want to do the molar flux of water. As if you remember from the last part where I made that its own variable because it was involved in, I believe, all the differential equations. So that is going to be equal to the mass transfer coefficient divided by all R times T gas. And then we're going to multiply that by, let's see, the partial pressures. So this one was the vapor pressure at the temperature of the water, so W. And the other one was just the total pressure. Oh wait, hold on. It's minus the total pressure times the mole fraction of water in the air. Alright, so now I believe we have all of the variables we want to introduce for our differential equations, and we're ready to actually just put in the differential equations themselves. So we'll start with, again, we want to go the same order that our function is in, so dy is equal to negative specific area times molecular weight times molar flux of water divided by total gas flow. Then we'll go on to the change in temperature of the water with respect to position, and that one was equal to specific area divided by liquid flow rate, which I think I just named L. Yep, L times the specific heat of the liquid, CWL. And then we're going to do times, and this one was the heat transfer of the gas to the water, so we'll go heat transfer coefficient times Tg minus Tw, and I need that in parentheses. And then, there we go. Alright, so heat transfer coefficient times the difference in temperature minus the heat that is taken away from the evaporation of the water. So that was, what did I call that variable? Heat of vaporization of water, so H vapor, times the molar flux of water. So that was the second differential equation we solved for in the last part. And now for the third, we'll call this one dTg equals a specific area times the heat transfer coefficient divided by total gas flow times Cg, Cg, not Cwg, times the temperature difference, Tg minus Tw, and now we have all three of our differentials, and that's what we want to return. And again, we want to return that. The important part is the order we return it in, so we want to make sure we return it in the same order that we call on them in the function. So dy first, dtw second, and dtg finally. Nope. dtg. Oh my gosh. dtg. There we go. Alright, so now we're out of that function. Let's see, we're ready to solve our IVPs, so we can say sol equals solve IVP. So first we want to give it a function, so we'll give it dy TW, TG, yep. Now we want to give it our t-span, so our t-span will be z plot. Or not z plot, well, what did we name z plot? Well, our t-span we can just say is 0 to height. So now we want to give it our initial guesses, which we know our initial guess for, or not even guess, we know our water going in at a position z is equal to 0, but the temperature of our water, but we don't know the temperature of the gas leaving, and we also don't know the molar concentration of water in that gas phase, so we'll have a little bit more work to do there. But we can kind of put just variables there for now, so we'll have y at the it's actually when the gas is leaving the cooling tower, so we'll say y out. I have TW is the one we know, so TW feed. And then we also don't know the temperature of the gas leaving, so we'll say T gas out. Alright, so now we have our initial guess. Let's see what's next. Method, so we'll do method equal to Radu, the same method we used in our first homework, I believe, or first exam maybe. And then we'll set dense output equal to true. And then we want to do, now here's where we have the solution in the range of z plot. And let's see if I shift enter. Invalid syntax. Let's see, what did I do? Oh, I think I added an extra parenthesis there at the end. Oh yeah, I definitely added an extra parenthesis. Shift enter. Y out is not defined. Oh, okay. So y out's not defined, but yeah, that's because we don't know our mole fraction there yet, so I'll come back to that. Alright, so this y out isn't defined. So we're going to want to make another function that's going to allow us to converge our guesses, our initial guesses. So we won't have this problem of it being undefined, so I want to define a function. I'll just say converge guess. And we're going to feed this a variable. We already used v, so we'll use v2. And that will take in our guesses, so y out, I believe I called it. Yep, y out. So y out will be equal to v2 and the first element. And then our second one that we don't know is tg out. So tg out will be equal to the second element. And then we're actually going to need that sol variable to be global, so it's not only available in the functions. So we'll just do global sol here. I don't think I capitalized this. It should turn blue. Yeah, there we go. Global sol. Alright. And we actually want this whole other function to be inside this big function. So I believe if I tab, yep. So now that whole second function, or the whole first function we made, is inside this second function. And then after this sol, we want to return the last bit. So here, I'll walk through. So we want to return from sol the last. So we want the first array in sol, but we want the last element in that array. So you do 0 for the first part of the array, and then the last number in that specific array. So, and then minus the feed. Let's see, I think YA feed, where did I put that? Yeah, okay, YA feed, which is our initial mole percentage of water in the air. So that's the first thing we want to return. And the second thing we want to return is essentially the same thing, but for the temperature. So that'll be the third element. Oh, geez. Third element in the array. Same thing, the last item in it, but we want to subtract out our temperature of the feed. So what did I name that? I believe it was TW feed, yep. Well, hold on. No, we know TW feed, so it was the gas that I want, which is T temperature of the air feed, TA feed. Alright, my return is done. Alright, so now I should be able to run this, no problem. Let's see. Yep, looks like it ran. So now I think should be able to do the root function. We'll call on our converged guess. And then I will feed that v2, so we'll do our initial guesses that we made from up here. So let's see. The first element I made the mole fraction, so y outguess, or ya outguess. There it is. The second one I made the temperature, so say TA outguess, TA outguess. Alright. Oh, so function comma. And let's see what happens when we run that. Oh. We're gonna stop that. Let's see, we got an error in here somewhere. Global sol. Alright, gotta try to find this error. I'm not sure where it's at. Well, I'm going to pause the recording and try to figure out this error. I haven't seen anything like this before, so. Alright, so I'm back. That was a pretty tough error to find, actually. So what ended up happening was, I think I misspoke earlier when I was solving for the flow rate, the gas flow rate of air. I said to divide by the velocity that we were given. When you actually multiply, I'm not sure why I said divide, but so I had that divide by velocity of air, and that ended up making one of my values in one of these arrays was 0, so it ended up when I was trying to do the root, there was a divide by 0 function, divide by 0 error that was happening, and it kind of freaked out a little there. So I was kind of hunting through to try to figure out what was wrong. I ended up finding it. So here we go. And then, as you can see, when I ran it there, it looks much better. The solution converged, and we have this array that is our converged converged answers there. So I think we're ready to move on to the graphing. So I'm going to make a variable figure, and we're going to do figure equals make subplots, and we want, let's see, rows, columns, we want 3 rows. So we have 3 differentials, and we'll just do it in 1 column. There we go. So now we'll do fig dot add scatter. Trying to remember, I think it's underscore add scatter. We want x to be equal to z plot, yep, there it is. Y should be equal to, so we want this to be the first element in our sol array. So, and then we want all the values since we're graphing it as it changes. And then I believe next we can name this one, and this is going to be the mole fraction of water in the air. So name y, and then we can set it, we want it to be the first graph, so row 1 and cal equal to 1. And now we just do the same thing for each differential. So we'll copy that, paste it on this one. This time we want the second element in the sol array, and that second element, remember we kept it as TW. Well, since we had 3 rows and 1 column, we'll make this row 2, column 1 still. Then we want to do the same thing, but for the temperature of the gas. So it's going to be TG, row 3, column 1. I believe if I did everything correctly, we should get some nice looking graphs here. Well, let's see, what did I do? Oh, okay. Column. Oh, what the? Should be pluralized. There we go. Oh wait. This one should not be plural. I don't believe. But we're about to find out. Let's see. Oh, there we go. I thought I made the background dark. Templates. Oh, I spelled default wrong. Let's see. Now I'll just rerun all the boxes. It should be dark when we get down there. There we go. I like that better. Alright, and this kind of looks a little tough to read, I guess might be the best way to describe it, because the graphs are so long. So you can kind of go, let's see, fig. We're going to update the layout, and we are going to change it to, what do we want to go with? I think 500 looked good, and a height, we'll say 800. Shift enter. And that looks much better. So if we want to take a look at the graphs real quick, and we can see that they kind of make sense with what we talked about in the past couple sections. So this first graph is the mole fraction of water in the air in the cooling tower. And if we remember, we named, yeah, okay, that was it. We named the top of the cooling tower as position 0. So position 0 is right here. So it makes sense. The air is coming in from the bottom and going out the top. So at position 0 at the top of the cooling tower, the gas should actually have the highest concentration of molar concentration of water. So this makes sense, and it comes into the cooling tower at its lowest. So this graph looks good. And then this is the temperature of the water, and the water is coming in at the top, and it's coming in hot, and it's actually being cooled by the cooling tower, which is what's supposed to happen. So this graph also looks good. It gets cooled a lot more than the gas heats up. So the gas is, again, it's coming in at the bottom. So the gas is coming in at its coolest temperature, and it's getting heated up, which makes sense as it's drawing heat away from the water. So the reason the water is able to get cooled a lot more than the gas heats up is that the water is also losing heat due to the heat required to actually evaporate the water. And that was why we included like the heat of vaporization in our calculations and in our differential equations. So that kind of wraps up exam 3. So thanks for watching.